pointer. Okay. Sorry for the short delay. So my name is Christian Turo. I work as a data scientist at a company called the Unbelievable Machine Company. And before that, I worked as a machine learning researcher for about 10 to 15 years. So, and this talk I think is a bit similar to the first talk that we had in this session. So I also want to talk about machine learning APIs. So this question was asked before also in the first talk. So actually, who of you have heard of machine learning before? So almost everyone, that's awesome. Who of you have heard of deep learning? Few. Artificial intelligence? Probably everyone. Cool, great. So, but let me give you still a brief introduction into it. So basically, machine learning is actually the task where you want to solve problems by using data. So one of the real successes of machine learning was in computer vision about 10 to 15 years ago, when we managed to detect faces in images. So here, probably something that you have seen on your smartphone or on your camera. So now, when you want to take a picture of someone, the face is automatically found in the image. So how does this work? So basically, you use a lot of data. So in that particular case, a lot of data from facial images. So this is what you use as training data, this is called. So you want to learn from examples how a face looks like. And then you sort of train a model, as we also see in the first talk. So basically how does work? So you have some algorithm, usually some masses involved, and then you try to extract or try to find out what actually makes a face, and afterwards you can apply that model to unknown data. So to detect faces that were not part of your training data. So you apply it to test data, right? So this is pretty simple in the case of faces, but recently we saw a lot of new applications and new good examples for machine learning. So for example, this year, I know if you heard about it, this guy real-time translation. Anyone heard about it? So this I think is quite impressive. So there was 2 years ago, people discovered a technology called deep learning. So basically it's not really new. It's based on artificial neural networks that we had in the 80s. And now we were finally able of using a lot of data to train really large networks. And that changed a lot of things. So one of the things that we're now able to do is something like that, where we now have a real-time translation. So that wasn't possible before. And now we can do that. And I really think in 2 years from now, probably, it will be completely normal for us to have sort of a bubblefish, so that you have some automatic real-time translation on your smartphone. This will be real. Or this one. Anyone have seen that example before? This is also quite interesting. It's from Google. So what you can see here is a couple of images. And then you can see what a machine that was trained with a lot of data on images and on descriptions and labels of these images, what a machine actually would label, how a machine would label these images. So for example, here, a person riding a motorcycle on a dirt road, right? So that in particular, when you don't know so much about machine learning, might not really seem like a huge thing. But when you have a look at computer vision and machine learning history, 2 years ago, we weren't here. We weren't even able of recognizing things like that. Even that would have been a great achievement. So having some recognition of something. But nowadays, this is almost solved. There even is a paper that appeared a couple of weeks ago where people claim that we now sort of reached superhuman recognition on these types of images. So now we can send an image to an API, to a machine, and it will return a description of that image. So we don't need humans to look at these images anymore. Another good example, this is from a company called DeepMind. So DeepMind was recently bought by Google, and they are currently probably one of the most well-known deep learning companies in the world. So what they did is they trained a deep neural network to play video games, these Atari games from the 80s. And it turns out that after some time, these algorithms are actually able of learning just from the visual input how to play these games. And they got really, really good at it. So now we have machines who can actually do a lot of things better than we can do them. So that's also why nowadays, when people talk about artificial intelligence, they usually mean deep learning by that. So this is not really the type of artificial intelligence we had, say, in the 80s or 90s or so, where we used some logical clauses, things like that. This is now all based on data. What you need for that usually is really huge amounts of data to train your models with. And then you come up with something which is really, really clever in certain ways. So what's next? I mean, probably all of you have heard of self-driving cars, but you think this claim here that in the future there will be, I'm really not sure if there will be any humans still driving cars. I think there's a huge risk in humans driving cars. So machines are obviously could be better at that, so they don't make mistakes. And now we have these machines who are capable of doing that. And one of the underlying technologies here is machine learning, actually. And to just end this introduction to machine learning, you might want to have a look at the interesting thought about the implications of machine learning. So there are really some interesting implications from that. And this talk is actually quite nice. It's a TED Talk from Jeremy Howard. So okay, going back to the real topic of machine learning APIs. So let's assume you want to use machine learning in your own applications or web applications. How do you do that? So as we also saw in the first talk, so there are a couple of technologies available. So the whole machine intelligence landscape is really, really huge nowadays. You have all sorts of different startups and companies providing APIs that you could use. I'm obviously not talking about all of these here. Actually, I just want to mention a very few. Or better, I only want to talk about certain tasks that have been solved that you could now easily use in your applications. So for example, for text recognition, we have things like sentiment analysis. So you have a couple of APIs for that. So then you can tell, okay, what kind of, exactly. And then we have things like spam detection, which is a fairly old application. You also have a couple of APIs for that. Language detection, topic classification. So these are all more or less solved problems here. And you have a lot more APIs that you can use there. And now, since there was a huge advancement for image analysis, you also have certain APIs for image tagging, face detection, and facial and emotion recognition. So what's a good thing about these kind of APIs is that they are using pre-trained models. So that means you don't need to know anything about, you don't need to know much about the problem. And more importantly, you don't need to use your own data. So you don't need to train your own models for solving or for using any of these applications. And best of all, of course, you don't need to have any kind of machine learning knowledge. And then you have a certain other, class of machine learning APIs. And these are just labeled here as more flexible APIs. So basically, there you have a lot more. So these are, I think, the most important ones at the moment. So yeah, there you have certain platforms and APIs that you can use to train your own models. You can use your own data. So let's assume you have a problem that wasn't solved so far. Then you can maybe come up with a good model and with a good solution to that using one of these platforms. And the good thing about this is that very little machine learning knowledge is required. So now we have a broad range of different platforms that you can use where you don't need to know that much about the algorithms behind that. So that's a good thing, I think. And you can even use your own data. So also from that perspective, well, that was close. Also from that perspective, I think that's a good thing. However, there is a certain disadvantage here. And I think all the platforms that we have here, all these APIs on platforms, they sort of oversimplify the whole problem once you have a new problem that you want to solve. So, and that is that the only thing they do and they offer is that you can train a model with them. So with these applications, you can now train your own machine learning model. But this is seldom sufficient. One thing that we found out during the last, say, 10 to 20 years is that the features are usually much, much more important than the model. So what are features in the context of machine learning? So let's assume we start with that example of wanting to detect a facial image, of wanting to detect a face in an image. So we have a lot of training data. Let's assume images. And then what you do, you extract features. So what's a feature? A feature is basically a numerical expression of the data that you have. So the most simple feature that you can think of in the case of images are actually the pixel values. So the grayscale or RGB values of the pixel. So every pixel has this grayscale value, and this you can use as a sort of input data to the machine learning model to train it. But these features are actually quite important. So you could, of course, just use the pixel values and then train the model. That would be the most simple feature you could think of when you want to do image recognition or face recognition. Unfortunately, this really seldom works out nicely. So how does it look like when you would like to, your typical machine learning task is actually a classification task. So what you have, you want to recognize faces from non-faces. And you have a numerical expression for that. So here we have a 2D space, and let's assume we have all the facial images here and all the non-facial images over here. So what would be your guess how would a good classifier look like that would actually be able of recognizing the two classes from each other? So in that case, it's actually super simple. You can just have a decision boundary here that would tell you everything in my feature space, which is on the left side is the face, and everything which is on the right side here is not a face. But this already gives you a certain idea how important that actually is. So the only thing that a machine learning model is doing is providing you this thing here, decision boundary. It doesn't tell you anything about the features that you need to put into that. So this here seems to be a very good feature because it's pretty easy to come up with a boundary, to come up with a classifier for it. But how about here? Now again, the orange dots are faces, the blue dots are non-faces. So this looks much more complex now. Now we have a feature expression where you cannot find an easy solution to the problem. And then you come up with something like that, the decision boundary. So the model that you train now looks much more complex. So there are two things which are important. The better your feature is, the less complex the model is that you need to train. And the second thing is, even if you want to go for a really complex model, and you will always find one that is perfectly able of classifying your training data, it doesn't mean that it also works well on novel or test data. So even then it makes sense to come up with a good feature. And it showed over the last 10, 20 years or so that the actual model, the classifier, so we have a lot of classifiers there, support vector machines, nearest neighbors, linear classifiers. The classifier is not that important after all. What is important is the feature, how you represent the data. So it's a bad feature. So going back to the images, so the pixel values, so the grayscale values of the image, this is a particularly bad feature as we found, and no one is using that. Do you have any idea how a good feature might look like for images? A good image representation? Actually, it's pretty hard to come up with that. So what you would do, you would apply some feature extraction, engineering, selection, and preprocessing, and this is a very long process. It's a very difficult process too. And it's not really a scientific process, right? It's not that you can solve that for it. It depends a lot on having a good idea about this. And this here is for some reason a good image feature. The interesting thing about this here is actually that this was found by deep learning network. So, and this is the reason why we are now seeing such a huge success in deep learning, in computer vision, and in all other fields, because deep learning networks are able of finding the best possible features that we know of. Before, people sat down and were thinking about how to construct the feature. And they would come up with something similar, right? But not quite as good. So people spend a lot of time just thinking about good features. And the computer vision literature is full of that. You really have the strangest features there. They are called hog and sift and whatever, right? Just to find a better expression for what you can see in the image. And this is what a machine found at the end. Unfortunately, deep learning only really works when you have a lot of data and only for certain problems. But you still always need a good feature. So how to find good features? That actually is a big problem, right? It works usually best when you have some knowledge about the domain. Think about the example about churn classification. When you have a certain idea why people in your business might churn, why your customers are churning, that of course can help you in constructing a good feature that makes it easier to compute a prediction about the remaining customers. And for other problems, of course, deep learning, I think it will be for the future the way to go, but it only applies when you have a lot of data. This is also what we saw now. You really need tons of data, otherwise the representation probably is not good. For other problems, it's really sad but true, but you probably need to ask a machine learning expert who has some experience with some of the data that you have, or you should have a look at scientific papers, because for all more or less common applications, you will find some nice feature representation, be it, I don't know, speech or of course computer vision. But this whole thing is usually not part of machine learning APIs, unfortunately. Right. So just to conclude with the talk, I mean, in general, I really think that machine learning is a fantastic tool which is now also ready for everyone to use in applications, in apps, on websites. It doesn't really matter. So we have a couple of problems that are now solved, like sentiment analysis, spam detection, face detection, and so on. And there are a couple of APIs that you can use. It's really easy to use them too. But in general, machine learning APIs are difficult to use. If you have to use your own data, then you have to do the feature engineering, or the problem is new or simply not feasible. So if you want to predict the stock market, you can apply whatever model you want. Basically, you will never have enough information to actually make or train a good model for that. This is probably what you can never come up with. Otherwise, I think people might have it already. Or, well, who knows? So, and for all the rest, I would really say that a customized machine learning solution is something that you should also consider. If you have a very specific problem, ask some experts to talk about the data, do the feature engineering, and then find and train the right model. I now skipped the part about the right model. I think I said it's not that important, and that's true, it's not that important, but it's still important to have a good classifier, but features actually way more important in that sense. Okay, thanks a lot for your attention.